Okay, so we talk about shortest path problem in a graph. So basically, what is a path? In a graph, this graph is a directed graph, a undirected graph, sorry, directed graph or diagraph. So we have a directed graph V comma E, where this E is the edge having the direction. So this is a directed graph. So let us take an example of a graph. So say V1, V2, V3, V4, V5 say. So there are say 5 vertices and say these are the edges. Suppose these are the edges. So this is our graph and we have a weight function on this. So weight function, we have weight on each of the edges. So that is the weight function. So suppose we have say -2, 3, -4, 5, then we have say -6 and we have say -1. Okay, so suppose this is the and suppose we have so this is the graph. Suppose this is the graph. Now what do we mean the path in a graph? So path in a graph means, so we take a vertex VU and we take a vertex V. So path from U to V is basically the, if we follow the direction of these edges, there must be some vertices. This is V0, then V1, then we have V2 dot dot dot, then we have Vk. So this is a path, physical path. Path, we denote this by P. Okay, so we start with the vertex U and then we take a edge, then we go to another vertex V1, V2 like this. So ultimately we have to reach to V. So this, if there is a physical path, then that is denoted, and weight of the path is basically, so we have the weight of this, so W V1 V0, this is basically W V2 V1. So like this. So weight of this path is defined as summation of the weight of the edges basically. So weight of the edges means sum of the weight of these edges. So summation of W Vi minus 1, and this I is varying from 0 to k. Okay. So this is the weight of the path. So basically Wp is basically summation of Wuv, where Uv is belongs to in that path. So this is how we define weight of a path. So we basically take the sum of the all weights in that path. So that is give us the weight of the path. Now the question is, now this is the problem of finding the shortest path. So when we can have a shortest path from a vertex U to V? So first of all, there has to be a physical path. For example, if there is no path from U to V, then there is no question of shortest path. So the physical path has to be there from U to V. So like if we say, if we ask for a path from say U is say, for this graph U is say V5, and if we take any other vertex say V2. So if we ask the shortest path, because there is no path from this, because there is no outgoing edge from V5. So V5 to any other vertices there is no path. So there is no question of shortest path. So to have the shortest path, first of all we need to have the physical path from U to V, if we have to have the shortest path from. So what is the shortest path? Suppose, so there has to be a path from U to V. So there may be many paths from U to V. So, among this path whichever will be the minimum weight, that will be the shortest path from u to v. Okay. So, among this, say there could be several paths from u to v. Among this path, if a path is giving us the, so that is basically, so this is basically WP is basically minimum among all WP such that, so this is basically denoted by delta UV. So, weight of the shortest path from, so you have a vertex u, then vertex v. So, this is basically minimum among all path from, so summation of, so this W is basically, WP is basically summation of u comma v, where uv in this path. So, minimum among, so if we have many paths from u to v, so P1, P2, P3 like this. So, if we have Pk, if there are k many paths from u to v, so then we consider weight of the path. Okay. So, if it exists, the minimum, this is not infimum, this is minimum. If the minimum exists, then we take that minimum. Suppose this PL is the minimum among all these, PL is the minimum of all WPI, I is from 1 to k say. Okay. Then Pi is our shortest path from u to v. Okay, let us come to this example. Suppose for this example, and that weight of the shortest path is denoted by delta uv. So, if there is no shortest path from u to v, then we denote this by infinity. If no shortest path from u to v. So, no shortest path means one option we have seen that there is no physical path from u to v, and there will be another option which is called negative cycle. We will come to that. Even there is a physical path from u to v, then also we may not have a shortest path. So, that we will discuss. So, let us take this example. Okay, so let us take this example. Suppose we want to find, this is a graph. Suppose we want to find the shortest path from, say V1 to V1 to V5. Suppose V1 is U is V1, and V is say V5. So, we want to find the shortest path from U to V. So, how many paths are there from U to V? So, there is one path we can go from U1 to V2, then V2 to V5. Okay. So, this is basically one path, U1 to V2 and then V2 to V5. So, this is a P1. So, what is the weight of P1? So, this is -2 -6. So, weight of P1 is basically -8. Okay. So, any other path from U to V1 to V5. So, yeah, so we can go from here to here, then we can take this, then we can take this. So, from here we can go to say V3, then from V3 we can go to V4, and then from V4 we can go to V1, V2, V1 to V3, V3 to V4, V3. So, what is the weight of this? So, this is 3. So, this is a P2. So, weight of P2 is basically what? So, this is -4, this is -1. So, this is basically -5. So, this is 2. So, weight of this P2 is 2. Now, is there any other path? Yes, we can go from here to here, then here to here, then here to here, then here to here. So, this is also one path. So, we go to V1 to V3, then VT through V4, and then V4 to V5. Yeah, we can write this path separately. So we can go to V3, then V4, then V4 to V5, V4 to V2, and then V2 to V5 directly. So this is say P3. So weight of this path is how much? So this is again 3, this is -4, this is 5, and this is -6. So this is coming out to be weight of this P3 is basically, so -10 plus 8, so -2. Okay. So similarly we can have another path like this. We can go from here to here, then here to here, then here to here. Again we can have here to here, here to here, here to here, here to here. But that will not not reduce the weight, because this is positive cycle. So it will just add the weight more. So why to take a loop? If there is a cycle here and this cycle is positive cycle, so there is no question of loop it into that cycle, because that anyway are going not going to reduce the weight again. Okay. So is there any other path? Yeah, we can go from V1 to V2, V2 to V3, V3 to V4, and then V4 to V5. So let us just try that. So we can go from V1 to V2, V2 to V2 to V2 to V3, and V3 to V4, and then V4 to V4 to V5, because if we go again V2, then again V6, that is -1, but still we have a -1 over here. So this is P4. So what is the weight? Weight is -2, this is 1, this is -4, and this is -1. So this is basically -6. So weight of this is -6. Anyway, you can think of, you can find out some more paths by taking the loop also, but that loop is, if it is that cycle is positive cycle, then there is no point in looping there. Okay. So among these there could be 3-4 paths which is taking care of this negative cycle, all these things. So among these, if we see, this is the minimum weight path. So this is -8. So that is the shortest path from V1 to V6. So the shortest path from V1 to V6 is basically, we go from V1 to V2, and then V2 to V1 to V5 is basically like this, and weight of this path is basically -6, and this is -8, and this is basically delta of V1 to V5. Okay. So this is the shortest path from V1 to V5. Okay. So this is our problem. Given any two vertex, we need to find the shortest path if it is exist. So when the shortest path will not exist, if there is no physical path from U to V, then there is no question of shortest path. If there is no path, then there is no question of shortest path. But even though if there is a path from U to V, then also we may not have a shortest path. If there is a negative cycle in the path, then there is no question of shortest path. For example, for this case, if we make this to be say -5 instead of +5, okay, or or this is, let us keep this +5, if just we make it to be -2, then we have a negative cycle over here. Then what we do? Then this 6, 8 may not be a shortest path, because what? Because if we demand this path is a shortest path, then we have another path. We can go from here to here, then here to here, here to here, here to here. So it is reduced -2. So as many times as we want, we can have a hop there, looping. Okay. So, if we have a from V1 to V from U to V, suppose, so this is a V1 V2, and suppose there is a vertex Vi where there is a negative weight cycle. This is negative. So, this is a Vi plus 1 dot 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 Vk. So, if there is a negative cycle in the path from U to V, so there is a physical path from U to V, but there is a negative cycle, then no shortest path will exist, because this will not converge. Because if you demand, okay, this -8 is my shortest path, so what I will do, I will have a loop over here, so that will reduce further. So, if you demand that will be my shortest path, then I will make another loop over there. That is that will, because that loop is negative. So, if we have a hop in that loop, every time we are going to reduce the weight. So, that way this shortest, their delta will not converge. So, that way delta of uv will be infinity for this case. So, no shortest path exists for shortest path from U to V if there is a negative cycle in the path. If there is a negative cycle in a path from U to V, then there is no shortest path from U to V. Okay. So, that also we have to take care, that there should not, I mean, if there is a negative weight, then we should able to detect that. Okay. So, now the question is, now this is our problem. Now this problem is called shortest path problem, finding the shortest path problem. So, how we can find the shortest path or length of weight of the shortest path. Okay. So, basically we want to find the delta. So, we want to see whether we can apply dynamic programming technique. So, for that we want to see whether there is an optimal substructure present in the problem. Optimal substructure. So, this is the first hallmark of dynamic programming problem, dynamic programming technique. Okay. Any dynamic programming algorithm should have these properties. The first hallmark is optimal substructure. So, that means what it is telling? It is telling if we have a solution of a problem, then it contains solution of the sub problems. Okay. Every solution of a whole problem will contain the solution of the sub problem. So, this is the first hallmark, and the second hallmark is repetition, I mean overlapping sub problems. So, there are many overlapping sub problems are there. So, let us check whether at least we have the first hallmark or not. Okay, optimal substructure. So, how to establish this? So, this is, we can use a theorem for this. It is telling any subpath of a shortest path is a shortest path. Okay. So, how to prove this? So, what it is telling? It is telling if you take a path from U to V, okay, suppose this is a, we take a shortest path, this is shortest path from U to V. So, say Vi dot 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 Vj, sorry. So, V1 V2 dot 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 Vi dot 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 Vj V. So, suppose this is the shortest path from U to V, this is basically delta of uv. So, this is the weight of the shortest path from U to V. So, this is a shortest path from U to V. Okay. Okay, now if you take a sub path, if you take this just this path from this is a sub path, this path only. So V1 to Vi to Vj. Now we have to prove that this will be the shortest path from V1 to Vj. Okay, so that is the optimal substructure. If you take this path, sub path from V1 to Vj in the shortest path of U to Va, then this will happen to be the shortest path from shortest path from Vi to Vj. So this is a sub path in this shortest path. So how to prove that? So to prove that, you have to use what is called cut and paste technique. So this we are going to show, this is the shortest path from, suppose it is not a shortest path from U to V. Suppose, suppose this part is P1. Suppose, so this is the proof. This is suppose P1 is not a shortest path from sorry, this is V1 to Vj, by Vi to Vj. Suppose it is not a shortest path from Vi to Vj. So there has to be a path which is shortest path. We are assuming there is no negative cycle and there is a physical path. So we are so there is a path from V1 to Vj which is the shortest path. So this is we are denoting by P star. Okay. So then let P star be the shortest path from Vi to Vj. Okay, we are assuming this P1 is not a shortest path. So there, so we are assuming that P star is a shortest path, another path. So what we do? So we take this as a this Q1, this path from this to this, and we take that path as a Q2 from this to this. Now we take this. So that means what? That means W of P star is less than equal to W of P1, because P star is shortest path from Vi to Vj and P1 is other path from Vi to Vj. So weight of the P star must be less than this. Okay. So now we take the path from U to V like this. So we take a path. So this is our original path. This is the P. So what is P path? P path is basically Q1 and then Q1 and then followed by P1 and then followed by P2. Sorry, Q2. Okay. So this is our P path. Now we take another path which is R shape, which we are taking instead of this P1 we are taking the P star. So Q1 then P star then Q2. Okay. So now what is the weight of R? Weight of R must be less than weight of P, because this P star is the shortest part of this, but this is not possible because we know the P is the shortest path from U to V. So that is the contradiction. So this technique is called cut and paste technique. Cut and paste. Cut and paste technique. So we assume this is not a shortest path. So we cut that one and then we paste a shortest path from that, and then we reach to a contradiction. So that means this theorem is true. So every sub path of a shortest path is a shortest path. Okay. So this is the optimal substructure. So that is the good news. So that is the hallmark for dynamic programming technique. So even second hallmark also you can easily verify. So now we will think of dynamic programming technique, but before that we want to see whether we have the powerful one, the greedy approach can be possible or not. So, for that we will see the greedy algorithm can be applied or not. So, for that we will take a inequality, another theorem which is called triangular inequality or triangle inequality. Okay, so basically what? Basically this is telling us for all vertices u, v and x belongs to v, we have this inequality. So, shortest path from u to v must be less than equal to shortest path from u to x plus shortest path from x to v. Okay, so this is called triangular inequality. So, how to prove this? So, this will give us the algorithm which is a greedy approach called Dijkstra's algorithm. We have to use this inequality there. So, let us try to prove this. So, to prove this, let us take, this is the vertex u, this is the vertex v and this is the vertex x. So, we are talking about shortest path from u to v. Now, shortest path from u to x and x to v. So, this is basically delta of u to x and this is basically delta of x to v and this is basically delta of u v. Okay, so this theorem is straightforward from this picture, because so if we take this, so this is the shortest path from u to v and delta is the weight of the shortest path. So, weight of the shortest path must be less than of any other path. Now, if you take this path from u to v, we go from u to x with a cost this, we take the shortest path there, then we go for x to v, we take the shortest path there. So, this is the path from u to v. So, and the cost of that path is delta of ux plus delta of xb. So, this is a weight of a path. So, this path has to be greater than the shortest path from u to v. So, that is the theorem. Okay, so, this is called triangular inequality. So, we will use this inequality to have the algorithm in our algorithm to finding the single source shortest path. We have given a source S and from there we will find the all shortest path from any other vertices. So, that is the Dijkstra's algorithm. We will discuss in the next class. Thank you.